Okay, welcome to the Early Career Research Seminar. Today's speaker is Trystan Lambert, who did his master at the University in Cape Town and is now doing his PhD in Chile at the Universidad Diego Portales. And yeah, Trystan, go ahead.
Thank you very much. Yeah, thank you, Christoph, and all of you for inviting me here today. I would really have loved to be there in person, but with these times, yeah, nevertheless, I'm still very happy to be presenting to you online. And I'm hoping that you get something useful out of this talk. For those of you who missed the introduction part, my name is Trystan Lambert. I'm currently a PhD student. PhD candidate at the Universidad Diego Portales in Chile, working on high redshift galaxies. But that's not what I'm talking to you today about. Today, what I'm going to be talking about is this work that I did throughout my honors and masters at the University of Cape Town with these great people here, Professor René Concordever, Thomas Jarrett, and Lucas Macri. I'll start by explaining what the tumor-S actually is. Then I'll speak about how we took the tumor-S, how we managed to find galaxy groups by modifying the well-known friends of friends algorithm to build a personal group catalog. And I'll finish off by explaining how we use these new visualization techniques to inform our process throughout the way, as well as our sort of final results. So let's begin first, the 2-micron all-sky survey. This is where it all started. This was a mission between 1997 to 2001. It was an idea to image the whole sky in HJ and K bands, so infrared, using the 1.3 meter telescopes at Mount Hopkins and CTI in Chile. And this is what the what 2MASS looks like. Basically, just one picture of the entire sky. From this, there was a point source catalog which consisted of 500 million stars and unresolved galaxies. And what's more interesting, I guess, to us in the audience today is this the extended source catalog, which consists of around 1.6 million extended sources. In other words, resolved galaxies. So we have this massive data set of galaxies with their 2D positions on sky. And when we're looking at large-scale structure, what we would really like is to have a 3D map of the universe. So this brings in the 2MASS redshift survey, which uses this 2MASS extended source catalog as the input mask. This is another image of this. This is an ATOF projection in galactic coordinates. You can clearly see the Milky Way along the plane, on the equator. And essentially, the idea here behind the 2MASS redshift survey was to go out and to measure each one of these galaxies and to get a redshift. Other types of catalogs exist. For example, the 2MASS Photo Z catalog that was done, but we want spectroscopic redshifts of these galaxies to build a really good 3-dimensional map of the universe, which then people could use for whatever they want. Before we took over this project, the latest data release had a magnitude limit of 11.75. It contained 44,500 galaxies. And this was the late, great John Hucker's final paper he published posthumously published in 2012. But that was incomplete. There were 1,041 redshifts missing, so about 2.4% of these galaxies didn't have redshifts. And if you look at the distribution of where these redshifts are, they all, not surprisingly, aligned along the Milky Way plane. Again, this is an ATOF projection. And of course, where the majority of them lie are here within this along the Milky Way plane, what's being called the zone of avoidance. And this is kind of where my group and the tumor-S group came in. Because of my supervisor at the time, who's an expert at observing behind the Milky Way in the zone of avoidance. And we were very interested to know what was happening here. So this galaxy sample of missing galaxies actually was really useful for us to actually go measure. So we took it upon ourselves to go and measure the remaining, what was called then the 2-mass missing redshift survey. So there's lots of terrible acronyms that came along the way. But nevertheless, we went out to observe these missing redshifts, about 1,000 of them. We did this one by one using the Fred Lawrence Whipple Observatory in Arizona, as well as a 1.9 meter telescope at the South African Astronomical Observatory. And we just sat and measured all these 1,000 galaxies or so. These were published in 2019, and we have, so the final now most complete whole sky redshift survey, magnitude limited whole sky redshift survey, it was published here. We have 44,572 galaxies. Our contribution was these new 1,041 redshifts, which was an additional 22.4%. But what's important here is this number specifically for our group was to look at this additional 18% completeness for latitudes less than 10 degrees. So in that Milky Way area, which is a big difference, at least near the zone of avoidance. And this is kind of the final signing off of this mission. So this is currently the state of the TMRS and is readily available for anyone to use, Macri et al. 2019. So we have a large 3D distribution of galaxies across the sky. And ideally, what we would like to do is to start looking for large-scale structure. And to do this, I mean, you can start looking for lots of things. You can look for filaments and voids and things like that. But what I was tasked to do was to look for galaxy groups specifically within this our redshift survey. And what many people do as soon as they need to look for groups is that they make use of the tried and true tested friends of friends algorithm. And this is an algorithm which has existed, well, yes, Hucker-Engel in 1982, and it's existed for so long that it's nearly become biblical. You can't really argue with it. And I'll explain briefly how it works. I don't know if you can see my pointer here, but basically what you look for is in a redshift survey, you start with a galaxy and you identify all the galaxies along the plane of sky which fall within some linking length. Then you take that same galaxy and you look for all the galaxies that fall within some additional linking length along the line of sight. And this is usually done in velocity space. How these linking lengths are determined are done here. We scale the plane of sky by the density. And seemingly the best way to do this linking length along velocity space is to just set a constant velocity. But ultimately what you're doing is you find friends, and then you find friends of those friends, and so on and so forth. And that's how you identify galaxies. And this has been around for 40 years this year. So it's stood the test of time. But when we ran this, what we found was there were certain problems that occurred that we wanted to address. So it is simple, but what it comes with these problems. One major problem is that you could find friends of friends of friends of friends, and it never terminates. You could find, given the wrong set of linking lengths, you could theoretically take your whole galaxy group and make it one massive. It would identify your whole catalog as one massive galaxy group. What we found was if you start running this algorithm, say in order of RA, if you then ran it in order of, or in a random order, or you ran it in reverse, or you start with a different thing, your results could be slightly different, which is not a good thing for your results to be dependent on the order in which you've ran things. It's very sensitive to your choice of linking lengths, and this is difficult because we could run it on simulated data, and we could try make a justification for linking links, and people could sit around and have sat around and argued for months about what are the best choices. But ultimately, there may not be a perfect choice of linking links that exist. You don't get any quantification when you run it like this. You just basically get this is a group, this is a group, and this is a group. Because it's so sensitive to linking lengths, you only find, if you have large linking lengths, you'll find clusters, and if you have short linking lengths, you'll find groups. It can't actually differentiate between the two of them. So what happens is that if you have a group and your linking lengths are too short, or what you can think of is fine-tuned to find groups, it will tear the large cluster, sorry, into many tiny little groups. And the reverse is true. If you're wanting to look for clusters and you have groups, what will happen is it will put them all together and make them one massive cluster. So it's difficult for us to differentiate by eye even what's a group, what's a cluster, and what really is the difference between a big group and a small cluster. But it can really cause some confusion algorithmically, and it doesn't identify substructures. So we endeavored to try and solve some of these problems. One of them, the first two, run away, not robusticity. We solved, well, I'll give you an example of what happens. So when you run away, we start with one galaxy, we find the friends of that galaxy. And if you imagine, you probably want this to be identified as a group. Forgive my low quality simulation. I'm sure you guys are much better at doing that than I am. But so there you would have theoretically identified the group, but you would carry on finding friends, and you'll find friends of those friends, and you would go friends and friends, and you'll keep finding friends until eventually what you would have is your entire catalog basically has been identified as one group, which obviously doesn't make sense. And the way we dealt with this problem, as well as the initial seed problem, is to basically provide hard limits and to look for galaxy, not friends of friends, but friends of the mean, which may not make sense now, but this is my little toy example. So we start with a galaxy. We have a priori set limits on how big groups can grow, which they not necessarily will grow that big, but what will happen is it will cut off at a certain point. And we find the friends of this one galaxy, and we update the center and then carry on looking for friends within that center. And what this does, doing it like this, setting hard limits, updating the center when you're searching, a very simple change, but what it actually effectively does, again, with this toy model, is it now begins to hunt out overdensities. Because if you start with a galaxy where, for example, the top part is overdense, that mean will migrate towards those overdensities. And so just by doing that, we already made the friends of friends algorithm slightly better. And because that it hunts out these overdensities, what we noticed was that it was a lot more robust to your initial seed. So you could basically start from, run it in whatever order you wanted to, and you were basically going to get the same results. So that was the first kind of improvements we did. And the rest of these improvements dealt with running linking length. All of these kind of come down to dealing with what are the best linking lengths. And we couldn't really decide or make a justification for that. So what we decided to do was let's just run a bunch of them and average them over and try to figure out if we can get something from that. And the way we did that was, for example, we'd start with large, big ones like we've seen, and you would find one group. But if you were to start with a slightly smaller linking length, what you might find was that there were two groups. So which one's right and which one's wrong, this becomes a problem. But what we realized was you could run multiple runs, and you could, as a way to display how these runs work, as a way to display the results of all these multiple runs, we could represent these results as a mathematical graph where the nodes represent the galaxies and the edges between the nodes represent how many times throughout multiple runs were these galaxies identified in the same group. And this is just a toy model. These were some of the original right off the bat results that we got. And the positional data here on these graphs mean absolutely nothing at this stage, but you can already see kind of what it's telling us. We kind of already see that there are two kind of groups, but they are kind of identified into one. Here we see there's a major group with like a kind of substructure thing like this. Again, the positional data here is meaningless, but just by looking at these mathematical graphs, we can already start to imply things into what we expect to see. So, so by running over multiple different linking lengths and averaging over, then it no longer becomes sensitive to the initial linking lengths, and that becomes a way for us. We actually use that sensitivity to our advantage. No numerics and quantification. Graph theory comes along with it. Multiple any kind of statistics or say connectedness values or average weighted values or things like this, they come with graph theory, are now available to us to quantify the group in some way. It finds both clusters and groups now because we can identify using these quantifications. One of the important things was something we called connectedness. It was very easy to identify when groups were artificially being glued together, so we could separate those, and we weren't shredding these clusters. So we take care of that. The one thing we did have a bit of issue was identifying substructures. So this is a real example. Our method for identifying substructures basically comes from taking a group which seems good, and we start removing the strongest lines until we get to the lowest. So we can't remove any more lines before the group disassociates. So in this case, it's 2. We have 2 substructures here. And then we go back to where the group originally was at 2. So in this case, there we can identify substructures. It's not a perfect solution, but at least it is something. It's a difficult problem to try and solve. And using this improved friends of friends algorithm, this is the final group catalog that we published in early 2020. And it is available for people to use for whatever they might want to use it for. For example, it could be used to estimate the local density field or build flow field models. I mean, at the end of the day, is that the data product is available. And as we believe, this is the most accurate and most complete Term-Arrest galaxy group catalog to date. And so that's how we worked with Term-Arrest, and this is how we've built the Term-Arrest group catalog. Now what I want to talk about is how we what we did to get there. And I just want to kind of mention, say, for this is a famous CFA strip. This is a CFA stickman. This is what large-scale structure looked like back in the 80s. This is what we would do. We would measure, get redshifts or get redshift independent distances, and you can plot them like this, and you look for over densities, and we see there's a cluster, and that's what we used to do. And the way that we have been doing that has not changed much in the way we look for these over densities. This is what we published. So we go from this and we go to this, and we think we've made a huge amount of progress. But besides increasing the number of galaxies that we have and putting colors, and sure, we can increase the data set. But ultimately what we're doing is we're taking these galaxies and we're putting them in positions, stuff like this. And so it's not much different. And, you know, it's 2022, things should be changing, and things have thankfully are changing. That we don't have to look at things the same way as we have been for decades. And this brings me to really discussing kind of the exciting and fancy stuff. That's talking about the IDEA Visualization Laboratory, which we use throughout the entire process, from the initial through processing, looking at the output, interrogating hundreds of hours of visual inspection in this lab throughout the entire project. And there's several tools that we use. So I'll go mention some of these tools, and I'll mention some of the other work that people are doing, and maybe you guys can think about how you might use it in your own work. So one of the very first things we started doing was using this thing. This is called the Cape Cobra. It is a $25,000 piece of equipment. It's a curved screen, Ultra HD. And you can see I'm flying there and flying through this data set. So this, sorry, now we take this, which is a flat 2D image, which you do, obviously, we've built so many techniques over the years to deal with 2D images. But now you take that, we put it in 3D, and we actually fly around and examine that data set live. So in the top panel there, I'm looking at the group catalog overlaid with the galaxy catalog. So you overlay these different catalogs, it becomes really powerful, and you fly around and you just explore your data set in a completely different way. I mean, it looks pretty cool. So I'm sorry if the video is a bit jumpy here, but just to show you the point. And there isn't really a comparison between a 2D plot of these galaxies versus actually going and flying around. There's the zone of avoidance that we passed. I'm sorry if audio is coming out of that too. Yeah, so this is the first thing that we did to start exploring these data sets and make sure that our groups were actually finding groups and not I don't know, doing weird things. And now you might say to me, well, that's all good and well, but it's only 180-degree surface. This is a 3D thing. It's a whole sky thing. It might not. That's not really the best thing to be done. Okay, in which case I'd say no problem, because we have another tool that we like to use and which we have used. This is the new and improved digital planetarium in Cape Town. For only $2.3 million, you can upgrade a planetarium, hopefully that already exists, and you put in, and you can actually take this data set and you can throw it onto the dome and explore and fly through it, similar to what I was doing before then, but now 180-degree 2-pi area, Ultra HD, and it's more collaborative. You can have tons of people there too. You can also, as you see, you can overplot data sets, so you could see how the Milky Way, how the local stuff is seen through in your data sets. Again, at the bottom, we have the actual group catalog overlaid with the galaxies. So this is, again, another way to explore the data. And in a way, it's much better, again, because you have more area, collaborative. I think the resolution is about the same. Try to play this video. So this is in the planetarium now. So we spent a lot of time taking weekly trips to the planetarium to do research, which we then would look through the data set, look through the things, identify problems, come back, think about ways of solving them, and then the next week we would go through the data again. So it was a complete iterative process the whole time. Now, something you might say is, well, okay, that's still good, but it's very expensive, and you need a planetarium to find it. And at the end of the day, something you can never escape here is that these things are still 3D projections on a 2D surface. Yes, the surface is curved. Yes, it's 180 degrees, But at the end of the day, you're taking a 3D projection and you're putting it onto a 2D surface. And this brings me to what was, I think, a shock to everyone, but was definitely the case. The absolute best tool, which came out of looking at all these different things, also happened to be the cheapest. So for a couple $100 and some free software, you can set up this virtual reality system, and you can explore your data sets in VR. And this is by far, in my opinion, the best type of visualization tool that we currently have. The main point here is that instead of having the projection effects that you'll inevitably have with any type of visualization, in VR, a 3D data set is a 3D data set, and you can explore it as such. So this is doing, again, I'm sorry if the video is clunky, but this is doing this very similar thing to what I was doing in the Cape Cobra, but now in VR. And there's something very interesting going on here. Is you see the different colored spheres. These are different group catalogs of this data set from other authors, as well as our own. And the great thing about now in VR, we can walk around or you can explore, and these group catalogs mix colors. So if we want to compare results to previous groups, we can put all of the group catalogs in here, and anywhere where it's sort of white, that's where we are all in agreement. And anywhere where there's a mismatch, you can immediately tell which group found the group there, which group did not, why is the positions different. And then you can look at the actual underlying data, the Tumor catalog itself, and try and figure out why. So being able to explore a data set like that versus, say, the traditional methods of chopping things up and looking at them like this, there's just really no comparison. And the other kind of serendipitous, this happy accident which occurred, was when we initially conceived these graph ideas. This was before we were really using the VisLab heavily, but once we did start using the VisLab heavily, like I mentioned before, these positions don't mean anything, but you can actually plot them in 3D space too, as well as the graph. So we represented those kind of mathematical graphs in 3D space like this. And this is very powerful because the graphs are giving us information about all the multiple runs with all the different linking lengths that we did. And we could actually use that information to come up with strategies, for example, the one looking for substructures and things like that, to you explore these data sets, you put in these graphs, and we realize that we can cut away edges. What happens when we cut away edges? What happens when we increase edges? What mistakes are we finding? Things like this. So in VR, we're looking at a three-dimensional data set in 3D. You're looking at your input, which would be the galaxies here represented as these points. You're looking at your processing, which would be these graphs that we managed to manifest in 3 dimensions. And you're looking at ultimately at your output, which is the group catalog, in this case, what we were interested in. And you can compare your output to other outputs. So you have input, processing, output, all being explored at the same time in 3D. It's completely natural to investigate your 3-dimensional data set in 3D. And the other great thing with virtual reality was that we could build tools that we wanted to do. So for example, I don't know if I can play this video again. For example, one of the nice things we wanted to do was to take these graphs and to actually remove edges, or to select which edges we wanted. We wanted strong or weak edges. That was a tool that we that you could do in VR. So we'll see now. Yeah, we can actually cut away the strong edges and see what are we can cut away the weak edges. We can see what are the strongest groups that exist, which we call cores. Yeah, so there's so much that you can do in VR, and you can build tools specifically that you need. Now, some of the other stuff that we did in this VisLab, and I'll just take a kind of detour here. Some of the other stuff they did in the VisLab was, well, this isn't astronomy related, but they put a mouse brain in VR, so people, and as well as in the planetarium, so we could walk around this mouse brain with a biology group who wanted to see which neurons were firing, which weren't, and I'm not sure if they got anything out of that, but it still was very cool to put it up. The main idea for the VisLab actually wasn't for the TOMRS, wasn't for particle data sets, it was for FITS data cubes. Many people will know that the SKA in South Africa is a huge data intensive project. And so it was actually invented for what we wanted to use these things was for radio data cubes. So any type of radio data, now what's normally what people do is we have a radio cube and we work out what a moment naught map is, we work out what a moment 1, moment 2, moment 8, moment -1, channel maps, PV maps. And we cut and dice these radio cubes up in as much as we can. And just to get this, but you can now, what the lab is currently able to do is to volumetrically render radio cubes, which is very impressive, and it's been used obviously on SKA data, on Meerkat data, and I have actually used this too for ALMA, looking at high redshift galaxies too. So again, this is just it's a brand new way to explore your data sets, which may reveal things that you haven't thought about before, or could at least point you in the direction of analysis. Another really great project which was done in the lab was this one. This was simulating two galaxies interacting with each other. So the simulation was run separately, it wasn't run live, but the results of that simulation could then be explored interactively. The nice thing here was that you could pause the simulation, rewind the simulation, do it frame by frame, look around it. You could select which molecules you wanted. So I think here it was gas, stars, baby dust. But you could color the particles based on their typing, so you could see what happens to the gas, what happens to the dust, what happens to the stars individually. And with this one, you could have people actually observer mode, where people could watch, say, a presenter giving a talk, pointing directly to what they're talking about, or a live mode. So you can imagine the difference between looking at a bunch of 2D, a GIF basically, which is what you would do to represent this, and then exploring it in 3 dimensions, live, pause, rewind, fast forward, color coding, and with any other statistical tools that you might want. Another great thing that people may be interested in is this flow field example. So this is looking at local flows. I think this comes from the Cosmic Flows project with Helen Quattar and Tully Fisher. And you can represent this again in 3D in VR. And you can see how the cosmic flows are in the local universe. And one interesting example is this. This was a cosmological simulation by Neil Katz, and where you can see the filaments and the voids. This is your kind of standard cosmological simulation. I didn't explain it, but the interesting thing here is you might not think it's all right. We've had these cosmological simulations for ages, and perhaps the author who wrote the code too probably thought too that all right, it's cool to look at things in VR, but what do you get from it? And a great example was he was flying around here and he identified this. He saw this weird thing that he didn't know what it was, and it was a ring galaxy, which he didn't know that his code was capable of producing. So that just goes to show that by I'm not sure how you would go about searching for something you didn't know your code was capable of doing, but even identifying in this case, identifying, or even what would you do to run searches for this thing? So in exploring the data like this in 3D, what you find is things that you didn't know, or weird behavior, things like this. So it's just really, really good to interrogate your data as much as you can. This was a cool example of his code doing stuff really cool, which he didn't even know it was capable of. This is an example of my code doing terrible things, which I didn't know it was capable of. But this is just an example of how powerful looking at your data sets like this is. We identified with the friends of friends algorithm, we identified, and using our graph theory, that these two obviously separate structures, one massive cluster, one kind of side group, were being considered a single group because of one single, I'm trying to identify a line, I hope you can see it, one single connection between the two. So in one type of run, this one galaxy managed to fit with this other galaxy. And if you were running the friends of friends algorithm once, in that case, you would have identified two obviously different structures and connected them like this. And so when we noticed that this was a possibility, then we could come up with solutions to this, which we did. And so that really goes to show the power of visualization of these techniques. It's not necessarily to say that everything was done by visual inspection. No, it's informing yourself every step of the way of the process, and then building tried and true methods to show to other people. Yeah, so that's what we did. That's what we did with VR. That's what we do with VR, and as well as other visualization techniques. This again, summarizing now, this is the TMRS group catalog that we've had, that's been published. We recovered all of the great and wonderful large-scale structures that people love. And when we compare to other catalogs of the same of TMRS, we find on average more. And we've found a whole bunch of new groups right near the zone of avoidance. Some of them seem interesting. These are let's say new group candidates, because of course follow-up will be necessary to prove. But those are those results, and I'll just come to the conclusions. So throughout this project, what we've done is we completed the TMRS up to a K-band magnitude of 11.75, 100% complete. It's the most, I think it's the most complete magnitude limited whole sky redshift survey to date. We found about 3,000 groups in the TMRS group catalog, which again we think is the most accurate and definitely at the time was at least the most complete, because we were the only ones using the completed data set. We came up with a new method, which we think is making the most out of the friends of friends algorithm. We had been using these cutting edge visualization techniques, which are now being used not only for our research, but for other research. And what we think is it will gain traction and become more and more commonplace. In the future, and we'll see if these things happen. What I would have really liked to have done is not only to have identified groups in this way, but also identify other large-scale structures like filaments, voids, and sheets. And there's definitely a graph theory adaptation to be had for filaments as well as voids. I would have loved to have published this as a Python package, but in the current state, I wouldn't. But in the future, it would be nice to have this published, that anyone could run this modified version on their own Redshift surveys. It's always been a interest of mine to fill in the zone of avoidance. So what we had done was started measuring even more galaxies now within this gap of the TMRS, and we may need to wait for another PhD student to come around, another fresh master student to finish those off. But there's also a ton of work being done on Meerkat, on radio data, of filling in this gap. So the more redshifts we get here, the better. It would be great to be able to do that. The new group candidates would be wonderful to actually try and verify whether or not these were groups with follow-up observations. That again would talk to our method working quite well. And it would be nice to have this group finder to be updated to work with radio data. Radio data is different to, say, a magnitude limited survey like we did, because you have intrinsic biases. You're looking at things with a lot of H1, at least in the case of the SKA and things like that. So it would be nice to update it to work on radio data, radio redshift surveys too. Yeah, and I think that's where I'll leave it. Thank you very much.
Thank you very much for this nice talk. Any questions? Well, while people try to think about questions, I will ask one. So have you compared your method with the Robotham 2011 S function, how he determines the optimal linking length for gamma?
Mm-hmm. Sorry, I'm just having a drink of water. Yeah. So in the paper, I haven't brought it up here, but in the paper we have definitely looked at the way that Robotham did choosing the optimum linking lengths, and we ourselves also ran a similar type of analysis on identifying the best linking lengths based on the analysis, as well as doing a mesh refined grid or something like that. I forget exactly how to say the name. But so yeah, we definitely did. We definitely had an attempt of deciding which are the best linking lengths to use. After we did the analysis, we found once we do choose through whichever method you find these optimum linking lengths, what we then do is then still search. So instead of, if you think of a parameter space of linking lengths, we run it over a area instead of a single point in that parameter space. But that area is centered on the optimum choice of linking lengths, which was informed with similar way that Robotham did.
Thank you. I see there was a question by Uyun first.
I have a somewhat related question, actually. So this new algorithm you proposed that uses the mean location of all the points that is currently in the group. I was curious because you said like one of the problems of friend-of-friend algorithm is that like there's no clear method of choosing this optimal linking length. But now in this new algorithm, you said like, do you need to now tune two different parameters, not only the linking length, but also this size where you're not allowed to have friends?
Yeah. Thank you. You're not meant to ask difficult questions like that. No, that's true. So one of the problems that it might look like is that you're introducing more parameters that you have to select. I think the thing is that the importance of selecting those parameters kind of reduces. It doesn't make a massive difference whether your maximum space a group can grow to is 1.5 megaparsecs or 2 megaparsecs, something like this. A reasonable choice will be okay, because you're running it over multiple times. That it doesn't actually constrain it. It constrains it over one run, but doesn't constrain it over multiple runs. So that limit you choose is really just as a fail safe. So you can still get these clusters growing larger than these hard limits that we've called. And in terms of the linking lengths, they are important for individual runs, but where they become less important is when you've averaged over multiple runs. So that's kind of the idea, is that we are kind of trying to dampen the importance of having a precise or idealized selection of parameters. So I hope that makes sense.
Right. Thank you.
David, you lowered your hand, so your question was answered in the meantime, or?
Yeah, I think that the answer to that question kind of included some of the answer of my question. So it's, yeah.
Okay, then since there's no other question, I will ask one. So how about the availability of the software and hardware you've developed for visualization? So hardware-wise, what do you use nowadays and what's currently still on the market? And software-wise, what would you have to get there?
Yeah, so what I would say is that well, first off, if people are interested in the specifics of the visualization, I would really recommend looking at the IDEA website, which is really good. And they have all the tools that they use and all the software that they use, as well as contact details. And I'm sure they're happy to either run it on their own system or help people set up. So I'll have shout out them first. And in terms of specifically for the VR, which is the most, it's the best one and it's the most affordable and obtainable for most people. It basically requires a computer with a really good GPU and a headset. So any, it's a gaming setup. It's a gaming PC and the headset. The software that we used to run these things was using the Unreal Engine, which I believe is free, as well as another game engine. So that essentially what you're doing is you're running these, you're building a video game to be run on the VR system using these gaming engines, basically. And I think at least in the case of Unreal, I believe it's free. So the software is free. And I think you have to run it through Steam too. But then what you really got to do is just buy the game PC, buy the headset, and you're off. But if anyone wants more details specifically on how to build these types of things, then the IDEA website or the Jarrett 2021 paper is really is worth looking at.
Yeah, thank you very much. I see Rodrigo has a question.
Yeah, thank you. So yeah, I was wondering whether with this new method, whether you had something to say about the local hole claims. I don't know if
the local void.
Yeah, no, the local hole. Like I've read papers that claim that by analyzing this 2 mass redshift survey, that we live in a 20% under dense region, which might affect the Hubble constant and so on. So
no, I'm not going to make any claims on that. So I haven't really looked into it deeply, but I think it would be maybe we should, because we have the group catalog, and at least Lucas Macri works a lot with the shoes survey for finding the Hubble constant. But it's definitely something that it could be used for. But personally, I wouldn't be able to comment.
Okay, I would comment that the 2 mass redshift survey might be too shallow to actually quantify this. Yeah, since I think it's up to out of a redshift of 0.1 or something. So you have a very sparse data set there to make any strong claims. It would be very difficult.
So there is this recent paper last year. I think they combined also the 2m++. I don't know if that helps, to be honest, but yeah, I mean, I was just wondering whether with this new method you have something to say other than, I mean, that contradicts or whatever.
Yeah, I think until people start using this method for larger, deeper surveys, I think Christoph's right here. The TMRS is complete, it's whole sky, but the payoff is obviously that it's very, very shallow. I think it's 0.03 redshift, so it's complete to about 250 megaparsecs. I think you can just about touch. So yeah, it might be too shallow, but so I think that's correct.
Great, thanks.
Okay, are there any other questions? If not, I think we can thank the speaker again, and maybe stop recording